Okay, thank you very much, Spring. So we were just chatting in the room saying how crazy it's been VCR, but let's focus on the talk. So the title is Social Dynamics, Control of Large Groups and Vehicular Traffic. And already by the title, you see that there are a lot of connections to the previous two very nice talks by Michael and Dirk, both good old friends. And let me immediately go and start discussing about the system I want to talk about. So the term social dynamics is used for many different type of applications that include animal groups, vehicular traffic, social networks, and crowd dynamics intended as pedestrian, as we have seen in previous talks. And there are a number of buzzwords, or if you want, important words that refers to how these systems may behave. And we heard quite a number of them also in Dirk's talk, like self-organization, clustering, consensus, and so on. I want to touch upon some examples of mathematical models that were represented this type of systems. So a small collection of examples, but there is one very famous model that goes back to Exelman-Krause. It's an opinion dynamics model and is so-called bounded confidence. So you have here equations that essentially says that the opinion of every agent is attracted to the opinion of the other agents. And the way in which it is attracted is that the interaction occurs just within a given radius. So essentially, I interact just with people that have an opinion not too far from mine. From a mathematical point of view, this may create a discontinuity because you see, you may not interact, and then as you move, you may suddenly interact. And I will comment on this in next slide. The typical behavior that you see is that of clustering. So even when you start with a lot of agents, they will start to coalesce on a finite number of clusters. And as you can imagine, these clusters are usually a distance bigger than R, where R is these parameters, so that essentially they form and they stop interacting with each other. You see, this is time, this X, and this is the position of the various agents. Another very celebrated model is the one called the Cochran's-Mail. In the Cochran's-Mail model, you have a second order model. So it's more thought, for instance, for flocks like birds. The position of agent I is given by the speed, and its speed, again, works with dynamics that is similar to the Exelman-Krause one. So essentially, agents tend to align their speed, but with the strength that depends on their distance. Indeed, the first motivation for the Cochran's-Mail was language evolution, so a form of alignment, but related to language. And what you would expect from this system is that asymptotically, all agents will tend to travel with the same speed, but they may have a different distribution in space. There are a lot of models coming from nature. This is an example proposed by indeed Pais and Leonard. Naomi is an engineer from Princeton working on a lot of different applications. And this is an example. This system is somehow not too far away from the Cochran's-Mail, but essentially has an additional component. So beside aligning our speed with our mates, flock mates, here the birds will also tend to align to a given speed. And this may mimic well what happens in a migration situation in which there is a preferred direction of migration, and birds tend to align to that speed, but also at the same time interacting with the other agents. And let me mention another one, a model that we proposed a few years ago. Essentially, we took this type of idea of coming up from Exelman-Krause, Cochran's-Mail, and so on, but we put on a different state space and more precisely on a sphere. What you see here is essentially very similar to the Exelman-Krause dynamics. The difference is that we do a projection over the sphere, because if you want to keep agents within the sphere, you need to make sure that the speed, their overall speed is tangent to the sphere itself. So you do a kind of projection. That's enough to generate a lot of different behaviors that include the periodic orbits and other dynamics, other solution that we call dense inequilibria, in which every agent keeps the same relative position to the other, but overall the system may rotate over the sphere. So this is like a brief overview of this type of models that are used in many different areas, including traffic. Let me point out the mathematical question that was somehow overlooked in a lot of the literature. So the matter of fact mathematically is that here you put a lower, strictly equal than R, and you can put even lower equal than R, but you see it's a term that when the agents I and J get a distance equal to R or above, suddenly changes in a discontinuous fashion. So that's why this right-hand side is indeed a discontinuous ODE. And there is a lot of theory for discontinuous ordinary differential equations and a lot of different concept of solutions, like classical. That would mean your function is differentiable at every time and verify no-lucid equation. Karateodori means for almost every time. Filippo and Krasowski refers to creating a differential inclusion related to your discontinuous ODE. And CLSS, that stands for Clark-Ledeyev-Sontag-Subbotin, or also called the limit of sample and hold, are essentially limit of Euler type solution, the one in which you keep your velocity constant over a time interval, and this is your, say, numerical parameter, and then you send that to zero. Let me skip stratified because it's a little bit more technical, but the interesting point is that many authors in the literature spoke about this solution, but indeed we can show that for all these definitions you may use, you essentially always have solutions, except for classical one, because classical one excludes even angles or change of speed, and that does happen in the Exelman-Krause model and the like. But uniqueness essentially does never hold for any of the definition. So indeed, when you talk about the solution, you have to be careful because you need to select one of them. The good point is that still for almost every initial data, you have uniqueness of solution. So this set of special situations where uniqueness does not hold is not that big of a set because it's zero measure set. Indeed, it's stratifiable, rectifiable, has a lot of properties. But in general, you have to be careful when you talk about the solution because it's not going to be unique in general. A very simple example you see even in the Exelman-Krause case, if you take R equal 1 and you put, say, 3 agents of distance 1, here are 4 possible Karateodori solutions, but there are 1 parameters families. You can have that the agents ignore each other, or you can have that ignore each other from some time and then they start interacting. And you see that they will start interacting this time. This farther angle, because of also the blue and the yellow agent, will start to interact. Or you may have the 2 agents interact and the other doesn't. All these are perfect Karateodori solution of your system. Again, classical don't exist. So the first solution concept that you get already violate uniqueness. But the situation is much more dramatic when you go to Filippo or Krasowski. All the solutions that you see here are Filippov solutions. So in general, if you move to next concept, like Filippov, you have a lot of different behavior, a lot of different possible finer clusters, a lot of different timing, keeping distance 1, and so on and so forth. It's even more dramatic because in most of these systems, people are looking for clustering. That means all the agents come together, but indeed for Filippov's solution, you may easily show that clustering does not necessarily occur. And the complexity goes to functional level for the space of solutions. So a word of care that even when we write down simple models, mathematically may be not completely trivial. But let me move on to the control part. Now, I will start first showing an application and then going back to something more mathematically oriented that probably resemble a lot or resonate a lot with what Michael presented in the first talk. So this is a joint work currently ongoing on a consortium called Circles, and it brings together University of California, Berkeley, Rutgers, Temple with Benny, our always present Benny, University of Arizona with Jonathan Sprinkle, Vanderbilt with Dan Work, and then various other partners, both companies and government, in particular the Tennessee Department of Transportation. So this consortium started this year, but really the ideas go back to many years ago when we started doing some research about autonomous vehicles. Probably you saw this movie too many times, at least some of you. But what we did here in this experiment is that we were trying to control traffic on a ring road with a single AV, 1/20, so it would be 5% penetration rate. So what happens is up to here, when everything was black, we have a single autonomous vehicle, but we were not controlling it. And waves were showing up. You see, the waves you see because the speed is going up and down. This is the speed of the autonomous vehicle, and the gray lines are the speed of all the other vehicles. But when we start using our algorithm to dissipate waves, we are able to do so. So you see now there is a red arrow. So the autonomous vehicle is doing some control via a computer. We designed the control, obviously, via simulations and other principles. And the interesting points are also the numbers that appears above that I will comment in a second when I will wait. Yeah, one more line. Okay, let me stop here. You see, the interesting point is look at what happens to these measures. For instance, the standard deviation in speed. It means how much there is speed difference among cars. When the experiment starts, there are small oscillation, but as waves are established, they go much up. And our best control almost destroys these oscillations. They reduce very strongly, both with respect to normal situation and waves one. But the fuel consumption is even more striking. The waves brought up the fuel consumption of probably around 30%, and we were able to break it down of more than 40%. So by just one autonomous vehicle, we were able to let all the fleet spare 40% of fuel. And braking events that are measured as a strong change in speed in a short time interval, they dramatically increased with the waves, and we essentially are able to cancel them. So this experiment goes back to 2016, and we were using just one AV. And you see the type of control we were using are not that different from the autonomous cruise control that already Michael mentioned. So we asked ourselves, okay, what can we achieve the same result with the current, autonomous adaptive cruise control that are available on cars? So for doing that, we got a fleet of 8 cars of exactly the same brand with the same ACC. And we tried to perform an experiment of what happens when you have a platoon of cars that are all connected one to the other using this ACC. So you see the first car is human driven, and we start to make a downward bump in speed. This will provoke a downward bump in speed of all the followers, but you see this downward bump in speed is bigger and bigger as we move forward on the platoon, up to the point that the last car, the white one down here, goes so low in speed that the ACC disengage. And in that case, we decided to put on our side. So the instability of currently commercially available ACC are so big that with just a platoon of 8 identical cars, you get to disengagement of the ACC. So indeed, what happens is that the current ACC are not necessarily designed to tame waves, so to reduce fuel consumption like we did in the experiment, but you really need something else to be designed and used. So now the consortium is aiming at bringing the logic we used on the ring road at highway level. And as you can imagine, there are a number of challenges there, and we are actively working on it. So let me move on now and go back a little bit to the more mathematical presentation and deep dive in some detail. Sorry about that, some detail. So first of all, let me go back to one thing that also Michael was mentioned, so the mean field approach. When you have a system, for instance, like the follow the leader band or other traffic system, you can rewrite your system in a measure theoretic way. This means that your ODE can be rewritten exactly if you identify your moving particles with moving Dirac masses. And so you generate what is usually called an empirical measure. And you define a kernel, an interaction kernel that is related to your dynamics. This may include, again, follow the leader, bando, or similar. If you do that, you can write indeed your system via a convolution operator that is defined here. Then you can pass to the limit, and then it's indeed an immersion more than a passing to the limit. If you send the number of particles to infinity, this becomes a general measure that solves an equation of this type, usually called Vlasov-Poisson. And this is, if you want a nonlinear transport equation, you see the convolution appearing here. And indeed, you see this is essentially the same equation. It's just that here you interpret as an ODE for an empirical measure, and here you interpret as a PDE for your measure solution. So what happens when you pass to the limit in the control sense? Michael mentioned some very interesting results, and but there are also some delicacy to that. If you just plug in, say, any control to your agent and you pass to the limit, you may obtain something that is very annoying. That is, the natural limiting term of your controls will appear in your limiting equations, but this may be an orthogonal measure. Orthogonal measure means that your measure may have no effect on d of the mu dynamics. Just to use an image, this would be like trying to control a river with a billion toothpicks. So probably you can use a billion or more toothpicks, but that's not gonna change the course of your river. So what are possible solutions? Let me mention three of them, and Michael mentioned already some. But one possibility, and especially fits very well our traffic problem, is control by leaders. So since the beginning, we do a multi-population approach in which we separate the population in two groups. A first group that for us are the autonomous cars that we can somehow control, locally or not locally, centralized or decentralized. But you see are equations that are written as before, but they have an additional term U here for the control. And then there is the rest of the traffic that we cannot control. Usually we want to keep this as small, like 2%, 5% penetration. Then formally, mathematically, we can pass to the limit, say in the bulk traffic, so the population we don't control, and we get a coupled system of ODEs and PDEs. And you see here the coupling because the mu that solves the PDE appear here, and the mu m that appear here is the empirical distribution related to these control cars. So similarly, you can define cost functionals that depends both, well, at the microscopic level at all the cars, and the macroscopic one both at the control one and the distribution. And you may obtain some nice results like a gamma convergence of the two functional. This means essentially that when you pass to the limit, the optimum of one functional will tend to the optimum of the limit. And this happens also for the controls. So you can use this result in two ways. You could design control policy at microscopic level and see what happens at macroscopic one, or vice versa. You can design, try to look for optimal policies at macroscopic level and then project back at the microscopic one. There are various other some result you can find here. It's in a publication with Fornazier and Rossi. Another very famous approach we heard from Sharon and other people is the one of mean-field games. Now, there are advantages and disadvantages. There is a very robust theory and a lot of very nice results. One limitation is that one big assumption is that every agent has a kind of perfect knowledge of the system. And so that is could be not obviously completely true in many situations. But the typical equations, I'm sure many of you knows that, are a coupling of two types of PDEs, one coming again from the dynamics of your system, but usually you add some noise that generate an additional diffusion term, and then another one that comes from essentially adjoint equations and are more of Hamilton-Jacobi-Bellman type. Again, you have a diffusion term here. The literature is really huge, both in terms of theory and applications, but essentially all the games started mainly from these two papers this approach of mean field games were proposed independently by a group of Peter Keynes, goes back in a paper 2003, and then the famous Lazary Lyons in 2007. And again, these were the starting paper, then many other appeared. Another way to try to control is refers to what Michael already talked about, and refers to the idea that you can put in relations control design at microscopic level with the effect that you have at Boltzmann or kinetic scale level. So the idea is that you can design micro model and guess what would be the natural interaction term Q. And you could say that, you know, a number of cars in your flow are AVs, so can be controlled. And when you pass to the limit, you can deduce the Boltzmann type equation or other expansion, and see what would be the resulting dynamic to achieve some effect at microscopic level. Again, Michael worked on this area, but many other people, and here you already saw the name of Zanella. Felicia is participating to this semester, and so on. So there are a lot of people that provided very nice results there. You know, I would like to spend some time now on a slightly more theoretical approach that is a framework I worked on more recently for trying to give a mathematical model that would work very much in the spirit of the mean field limits, but would possibly connect even more the microscopic and the mesoscopic scale and allow for non-stochastic model of uncertainties. So I need at least two main ingredients to discuss that. One is the Wasserstein metric. So I need to introduce at least some of the definitions. So the intuitive definition, this metric is also called the earth mover in research, operational research. And essentially what is defined is the following. Well, at a discrete level, you can define in a simple way. Given, say, a number of dots that you put, for instance, on the plane, the blue dots, and the same number of red dots, you want to find the best way of moving the red dots to the blue dots. The best way means that the way in which the total distance that is covered by all this movement is minimal. And you see, in this case, would be the solution, right? Well, I moved the red on the blue, or the blue on the red. It doesn't matter. You can revert the arrow. But you can define the same thing in a product space. What I mean is the following. You could place, for instance, if we are in R, assume these are the blue dot and these are your red dot. Instead of indicating your solution as arrows, you may imagine that you have like a matrix solution in which you put the green dots on the product space where they should go for moving a blue dot to the corresponding red dot. Again, in measured term, or in more mathematical abstract term, this representation is like a function. Every red dot goes to a blue dot or vice versa. This is like some object on the product space. You put a dot where connecting the two dots should go one into the other. In mathematical terms, you see this object as a generalized function or a probability distribution on the product space. And that's exactly what you need to do to solve theoretically the problem. So the so-called optimal transport problem defined in Wasserstein metric goes back to the 1781, proposed by Monge, and it was characterized as follows. If you have two measures mu and nu, and the cost function that could be just, for instance, the distance to a power p, you want to find an optimal map that move one measure over the other. So in the representation with dots, move means exactly you move some dots over the other dots. And so that you minimize, you take the influence, so you minimize this cost that you see, it's all the distances run by every point to their image. Forget about this p, is just, as a mathematician, we like to put p's here and there. But this problem in general don't have a solution. So the solution, the proposed solution came from Kantorovich and is based on the idea of generalizing from functions to probability distribution on product spaces. So essentially, you, as I showed before, instead of having a function, you have a probability distribution that move one mass over the other in the sense of the graph. And this allows you also to solve the problem of non-existence of solution in this case. So here you have always existence of solution under very mild assumption. And the resulting minimum value is called the Wasserstein metric. So again, it's the same as the earth mover, but mathematically you can characterize in a very nice way. Because of his work in this area and application to economics, Kantorovich, by the way, won the Nobel Prize in economics. So the other ingredient I need to use to explain my theory is a little bit of language from differential geometry. So let me try to go through that. So first of all, a manifold. I hope every one of you is kind of familiar, or if not, a manifold is essentially something that looks like is diffeomorphic to Rn, means that looks like some Euclidean space appropriately, say, banded, for instance. Obviously, this concept is very much used in the theory of relativity or general relativity, but essentially cylinders, spheres, and other hyperbolic surfaces are manifolds because you see locally it's like an Euclidean space, in this case a plane that is banded. Then an important concept are the tangent space. So at every point you have a tangent space, and I mean this goes back to the natural concept you have when you see a sphere in the space. For instance, you take a point, there is a plane that is tangent there, but mathematically it means that those are the speeds, so that if you move along those speeds, you will still be on the sphere and you will not get out. So an element of a tangent space is indeed a couple, usually a point in your state space plus a tangent vector that you indicate as v of x. It's important to keep this in mind. And if you collect all these tangent vectors, you generate what is called the tangent bundle. That means a collection of all these couples of points and tangent vectors. I will not go into the geometry of tangent bundles, that could be complicated, but with just these two concepts, well, this refers to the triviality of the bundle. If we stick to Rn, the bundle is just like an R2n. And in this language, ordinary differential equations amounts to assigning a vector field that is also a section of the tangent bundle. So essentially, if I assign at every point a speed that is tangent to the manifold, is like defining some equations for the evolution of your system. So having in mind this, okay, so let me again stress, I'm gonna see many times ODE identify a vector field that is seen as a map from every point to a vector, but I always, in differential geometry, I always think to those maps as a map from a point to a couple, that is a point itself and the vector, because you want to insist to say that the vector is applied precisely to that point. Using that language, you can define in a very natural way. First of all, you can define an ODE again by just a map from your manifold to the tangent bundle, associating to every point a vector, or better, a couple point vector. And by the natural immersion of points into, well, of your manifold into the space of probability measure over your manifold, can be done by identifying every point with Dirac masses centered at that point. So you see, this map can be read in terms of measure as a map associating to every Dirac mass centered at the point x, the Dirac mass on the tangent bundle centered at the point x Vx. So once you accept this language, then it's very natural to say, okay, I do that, so I associate a measure on my manifold to a measure on my manifold, a measure on the tangent bundle. Why I cannot do that for measures that are more general than Dirac masses? I can definitely do that and define maps that are associated to every measure on the base space and measure on the tangent bundle. The only requirement you see is going to be the following. Here, a key point is that the vector is applied to the point. So when you look it in the tangent bundle, the point lies just above your point on the base. Or other way stated, if you project back down to the base, you find back your point. The same thing should be true here. If you consider a measure on the tangent bundle, then this shouldn't be any measure, but a measure that projects down exactly to your initial measure. This is a necessary requirement to have a physical sense, and the values on the fiber would represent exactly the speeds along which you assume that your mass on the base should move. So we define a probability vector field as a map from the space of a probability measure on the base, in this case for simplicity Rn, to the space of probability measure on the tangent bundle, with the requirement that if we compute v of mu and we project back, we recover back mu. Once you define this simple object, you can define a measure differential equation by saying, well, my measure should move in these directions, and the meaning, as usual with measures, is in weak sense. So in weak sense means that your equation is just satisfied against test functions. So if you integrate your measure against the test function f and you take the derivative in time, then this is the expression that should satisfy. This is the gradient of your test function that is smooth, so this exists. You multiply it by a mute variable v, and then you integrate over the tangent bundle against the measure that is precisely v of mu. This may seem a little bit more complicated language. Well, probably it is. But the good point is that if you write an ODE and you write a vector field in the usual sense, so this would correspond to just restricting to Dirac masses, and you write this concept of solution, you find exactly the concept of Karateod resolution. So this generalization is absolutely natural and compatible with all of ODE theory. That's why it's also amenable to address multiscale and mean field limits. We developed a general theory for this type of equations. If you're familiar with ODE theory, essentially what you need for existence of solution is continuity of your vector field. This is Peano theorem. And if you want global solution, you need some form of sublinear growth. So your functions cannot grow more than linearly if you want global solutions. And the situation here is exactly the same. So the sublinearity condition must be given in terms of the support. So this is just, I'm taking a sublinearity condition looking at the support of V of mu compared to the size of the support of mu. And the second point is just continuity. Now we don't have a vector field, we have a probability vector field going from, for instance, a compactly support measure in Rn to compactly support measure in on the tangent space, on the tangent bundle. And we need this to be continuous with respect to the topology given by exactly the Wasserstein matrix I introduced in some previous slides. So this is exactly the correspondence of Peano theorem, and the continuity has to be intended for the Wasserstein matrix. Now, the other very famous theorem is the Cauchy-Lipschitz theorem that tells you that you have a unique solution if your function is also Lipschitz continuous. One of the probably most famous results in ODE theory. Now, the situation here is a bit more complicated because we are dealing with weak solutions. So weak solutions are very good for existence and very bad for uniqueness. So it's what you need to do is to look for solution for uniqueness, not at the level of a single solution, but at the level of a semigroup. So does it exist a unique Lipschitz semigroup? And if you think to that, it's very similar to the situation that you have in the Di-Perna-Lyon theory, where uniqueness has to be understood at the level of the collective equation and not of single particles. But you can recover uniqueness of the Lipschitz semigroup. It would be nice if that could be recovered by just asking this map to be Lipschitz with respect to the Wasserstein metric. Unfortunately, it's not enough. One needs to do something a little bit more esoteric and introduce a new functional that unfortunately fails to be a distance, but essentially works as follows. You see, take two if you want, tangent vectors in this generalized sense. So these are measures on the tangent bundle. And you want to measure their distance somehow. So you consider all maps, all transference plans that move one measure over the other, exactly as where we define the Wasserstein distance. Now, if I would write here the infimum over x minus v, x minus y plus v minus w, this piece would be exactly the Wasserstein distance. But instead of using all transference plans, if you want all functions in case of Monge problem, I'm using only those that on the base are optimal. So the ones so that on the base optimally move my original measure mu1 to my original measure mu2 in case of a probability vector field. In this case, these are just the projection of v1, v2. So in a nutshell, I need to pay a price of using a more complicated concept of uniqueness, but I can state a very similar condition as in the Cauchy-Lipschitz theory, and more precisely, if I have a Lipschitz condition with respect to this functional, again, it fails to be a distance because it doesn't satisfy the triangular inequality. But if I have a Lipschitz type condition with respect to this functional, then I do recover the existence of a Lipschitz semigroup. Uniqueness of a Lipschitz semigroup is a bit more complicated, so I will not enter into those deep woods, but rather leave more space for questions. Thank you very much.